Welcome to the narrated PowerPoint for Laboratory 10 for BBE 4023 Process Control and Instrumentation. The topic this week in lab is control using on-off control and the PDAC 55 and a Type T thermocouple. You will work in groups to use DAISY Lab to control the temperature in a box. In one case, you will be measuring the air temperature in the box and using the measured temperature to turn a cooling fan on and off. In the second case, you'll be measuring the air temperature in the box to turn a bulb on and off to keep the box near the set point temperature. You will also be asked to answer several questions. The purpose of Laboratory 10 is to implement on-off control concepts including set point and switching differential. You'll use a PDAC 55 and DAISY Lab to implement computer control to cool a space or to heat a space. You'll use relays to turn on and off either a fan or a light. And you will use temperature as the measured input for control. You will work in small groups. Each group will write one report, which will involve answering about 12 questions. The report is due at the end of lab. The box represents a space. The space could be a building or a room. The light bulb is the heat source. In animal housing, the animals produce and give off heat. In a classroom, students produce and give off heat. And in a house, the furnace can be the heat source. The fan, represented by the 4 black blades in the right side of the box, illustrates airflow through the space. The air exchange can be fan-driven or natural ventilation. The blue arrow is cold, fresh air coming in, and the red arrow represents warm, stale air leaving. A controller for the system will measure the temperature and use that to either control the heat source during heating or to control a fan during cooling. Here is a block diagram that describes the 2-position heater control. This was covered in section 14 of the course packet. If the error, the temperature difference between the set point temperature R and the measured temperature B, is less than 0, it means that B is greater than R, so the air temperature in the box is above the set point and additional heat is not needed, so the bulb will turn off or stay off. As the air temperature in the box decreases as cool air enters, the error will reach a value greater than the deadband or switching differential. This means that the box temperature is lower than the set point by D or more. At this point, the bulb turns on to heat up the box. In cooling mode, the cooling fan is off at low box temperatures and is turned on at higher box temperatures. In cooling mode, the fan turns off when the temperature difference between the set point temperature R and the measured box temperature B is greater than 0. When the difference is greater than 0, it means that B is less than R, so the air temperature in the box is below the set point and cooling is not needed, so the cooling fan will stay off or turn off. As the temperature in the box increases, the error will reach a value less than minus the switching differential D, and the fan will turn on. This means that the box temperature had risen to more than the differential degrees above the set point temperature. Deadbands or switching differentials are a small temperature difference between when equipment is turned off and when it is turned on. Switching differentials are used to avoid rapid cycling of the equipment. Rapid cycling is hard on equipment, especially motors. When you use 2-position control with a switching differential, there is always some error because the temperature cycles above or below the set point temperature. If the sensor sampling rate is slow, the system can overshoot. With a large switching differential, there is less cycling, but there is more error or difference from the set point. With a small switching differential, there is more cycling, but there is less difference from the set point. In lab, you will use a cardboard box to represent the controlled space. A light bulb will be the heating source. An exhaust fan in the wall blows the warm air out and draws in cooler room air into the box. You will use the thermocouple to measure temperatures with the PDAC 55 unit. You will program the DAISY Lab software to use on-off control for both a heating application and a cooling application. The PDAC 55 will measure the thermocouple temperature, compare it to your set point, and then send out control signals. The control signals will be used to turn solid-state relays on or off to control both the fan and the light. You may want to remember that the Type T thermocouple is a double-ended input. For this lab, you will again use a digital output as the control signal. You did this for the actuator lab when you used the PDAC 55 unit and DAISY Lab to send a control signal to the ISCO sampler to begin taking water samples. So you'll be using 2 digital outputs to control the 2 relays. connect to the cooling fan and the light bulb heat source. Here is the wiring diagram that will be in the lab handout. Off to the upper left is the Type T thermocouple, which is attached as a double-ended input to the PDAC55 unit. At the top center and right are the heat generating lamp and a cooling fan. They both are plugged into 120 volts AC power through the load side of two separate solid-state relays. The control side of the two solid-state relays are connected to digital outputs of the PDAC55 unit and to a 5-volt DC power supply. For this lab, we need to use reverse logic to control the solid-state relays because the PDAC55 unit does not have enough power to switch the relays we are using in lab today using normal logic. Normally, most of us would think that a logic 1, which is roughly plus 5 volts DC, would turn the fan on or light on, and that a logic 0 would turn them off. But we need to use reverse logic, so a logic 1 or plus 5 volt DC will turn the devices off, and a logic 0 will turn the devices on. As I said before, we need to use reverse logic because the PDAC55 unit cannot supply sufficient power to switch these solid-state relays. The PDAC55, however, can absorb or ground a plus 5 volt DC source, so we can use that capability to control the relays. The way solid-state relays work is that they turn the load or output side on when the voltage difference between the control side terminals is 3 volts or more. If the voltage difference between the control side terminals is less than 3 volts DC, the load side will be off. Greater than 3 volts DC, the load side will be on. So to use reverse logic, the plus terminals of both relays are connected to the plus side of the 5 volt DC power supply. When the negative terminals of the control sides of the relays are at plus 5 volt DCs, the relays will be off. When the negative terminals are at 0 volts, then the difference is greater than 3 volts DC, so the load side of the relay is turned on. Here is another slide that says the same thing in words. For the cooling case, exercise 1 of the lab, the light bulb heat source is always on. The temperature is measured for control to turn the fan on and off. When the fan is on, it sucks in cooler room air and cools the space. When the box is cooled off, the fan is turned off. As the air in the box warms up, the fan turns on again. For the heating case, you'll need to change light bulbs. In this case, the fan is always running to ventilate the airspace in the box. In the heating case, the light bulb is controlled, turned on and off, to add heat into the box. You will use a comparator again, as you did with the ISCO sampler exercise in the actuator lab. This is where the decision is made. Be sure to note that DAISY Lab uses the word hysteresis instead of deadband or switching differential. There are 3 boxes, so there will be 3 groups per lab session. Larger lab groups will be broken down into subgroups. You will submit group reports with your answers to the 12 questions at the end of lab. Be sure to list everyone in your group on the lab report and label your answers clearly. This is the end of the narrated PowerPoint for Lab 10. Please write down any questions you might have and bring them up in lab.